we will start so we have described what is density, what is functional, and today we will see what is actually density functional theory. Now density functional theory is basically a version of quantum mechanics where single particle density is the basic variable. Okay, that means rho r is the basic variable. Okay, so this is also quantum mechanics, like although some people call this semi-empirical etc. No, this is also quantum mechanics. Analytically proven theorems are there. So this one is the basic variable. Instead of the many particle wave function, so we are not using many particle wave function, nor we are using one particle and two particle density matrices. That's also problematic, isn't it? So if you don't use wave function, if you don't use single particle and two particle density matrices, only single particle density function, and you try to develop the quantum mechanics, that is your density functional theory. Okay. So how will you develop? But before going into this, why at all we should bother about density? We will see that since the advent of Schrodinger equation, like starting of quantum mechanics, people have been trying to develop a quantum mechanics only in terms of density. It is as old as the actual wave function based quantum mechanics when Schrodinger had given his own equation. I will tell you that precursor to modern DFT, that also I will tell you now. But before that, let us analyze why density is so important, why we think that we should talk in terms of density. So there are several reasons, but I will tell you some important reasons why density. If I ask, so one, experimental quantity, density is an experimental quantity. You can measure it like using crystallography. So there is what we can say that this particular object has the feet on the ground, so we can see that person. The other one you don't know where it is, 3n variables, or if you consider spin also 4n variables. Okay. So this is experimental quantity. 2, easy visualization. I can draw pictures. So easy visualization. Then you can have rigorous models. And you can say ad hoc qualitative models you can discard. You can develop various models which are rigorous because based on quantum mechanics. Then you can have drastic reduction in computational labor. so that we can now think about tackling or doing, let's say, electronic structure calculation or even geometrical structure calculation of very, very large molecules, which is almost impossible within wave function based picture or, let's say, density matrix based picture. Okay, so that is, in fact, this is one of the most crucial one, so that today we can talk even like DNA, protein, etc. We are doing all sorts of calculations, but you can even, it's wild to dream of solving Schrodinger equation for a protein, let's say. Okay, so you have to do so many approximations. Ultimately, the result what you get, that result would be a garbage. But density based mechanics can give you the proper answer. Okay. So now it's fine. First we will talk about the use of density in developing a quantum mechanics. As I told you, it is as old as the quantum mechanics per se, like the advent of Schrodinger equation and others. So, given Schrodinger had given that equation, but so the first one I will tell you. Remember, this is independently, it was given by Thomas and Fermi. So this is called Thomas-Fermi theory. Okay, this is a statistical model. But here also variable is the density. But this density within, let's say, some volume element, it is homogeneous. Homogeneous means you can get even simply by number of electrons in that volume, by that volume, n by v is your density. You know, this is your classical school level physics. You have learnt what is called density, isn't it? There you call mass by volume, here I am telling number density, number by volume. But here you can see that although it is as old as your Schrodinger equation, like 26 and 27 maybe, 1926, 1927. So this is still valid. You know, this is what we call homogeneous electron gas. So if you solve today, in modern DFT also we use homogeneous electron gas, or in the hierarchy we call it local density approximation or LDA. Okay, so you get like LDA, which is still in use as the precursor, and this is very important that analytically you can prove several results. It may not be as accurate as far as numbers are concerned, but you can see the qualitative features very well. This is a local density approximation. Not only that, today you can see, how many of you have heard the name orbital free DFT? Do you know this is another important branch that you must search and check? Orbital free. So in standard DFT we use cone-sum orbitals, but if you don't have any orbital, like I will tell you, I will show you the equations where orbital picture is not invoked. There still we make use of like Thomas-Fermi kinetic energy, and it is now becoming almost as popular as the standard cone-sum DFT. Okay. So what is Thomas-Fermi theory? Here the electrons are distributed, say, with different momentum range. Statistically you can apply like say Maxwellian statistics, Maxwell-Boltzmann statistics, and find out in a given range of momentum, let's say how many and what is the density locally, and there you can develop. If you go for it, the kinetic energy density This is called Thomas Fermi constant. So here you can see this is a functional. This is your kinetic energy functional. But this kinetic energy functional, you see, I am not bringing any differential operator. It is written only in terms of density. Okay, so this is a density functional. You remember, J of y I have written is a function of x, y, y prime integral a to b. That is the definition of a functional. Here you have, this is your a function of y integration. So this is a functional. You understand? So this is Thomas Fermi kinetic energy functional. Okay, this is your TAKE, Thomas Fermi kinetic energy functional. Now you think about several electrons. What is the external potential? External potential, let's say if I write V of R, it would be minus Z by R or minus sum over alpha Z alpha by R alpha. This is for atom, this is for the molecule, this is your external potential. So if I want to calculate external potential energy, this electron nuclear, so this would be your integral V of R rho R dr. This we have already seen, isn't it? V of R rho R dr. Then suppose you have electron-electron repulsion. Electron-electron repulsion, they also consider that electrons interacting with some smeared out charge distribution. That means there the operator is your Hartree operator. So if I call this as the Hartree operator, J of rho, this is your integral rho R, we will call R prime, let's say R minus R prime dr prime. Okay, but this is J operator. I am not writing this as a functional now. J operator is this. This we have already seen, isn't it? It is your so-called Coulomb operator. This measures what? The repulsion between an electron and some smeared out charge distribution of density rho of R. Okay. So what would be the corresponding Coulomb repulsion energy? It should be integral. So this one, J of R multiplied by rho R dr. Isn't it? This is one body. So again rho R dr. So altogether it becomes rho R prime R minus R prime dr prime. But here you can see R equal to R prime and R prime equal to R. In order to avoid this, I put a half factor. So this is your Coulomb repulsion between one electron and the remaining electrons as the smeared out charge distribution. This is nothing new. This it was there in Hartree. So this is in a sense your V electron-electron repulsion, but we will see that V electron-electron repulsion actually is different from this one, because there in V electron-electron repulsion you have here you have non-interacting electrons, but there you have interacting electrons. Okay. So you have to take care of that. In addition, you have to take care of Pauli antisymmetry principle, which is not there. Okay. So, and you know, if you take total the electron repulsion and subtract this one, that was the contribution of Fock, that is your exchange energy, isn't it? So now we will see that exchange in Hartree-Fock sense and exchange in DFT sense or Kohn-Sham sense, they are different. How they are different, that will tell as we go along. But there is no exchange coming per se in Thomas Fermi theory. Okay. So what you see, your ETF rho is T TF rho so this is your energy, Thomas Fermi energy, and you know how to get it. Your del ETF rho minus mu integral rho dr minus n is equal to 0, and that gives me del E TF rho del rho equal to mu. And what is del E TF rho? I have told you how to find out the functional derivative. So you remember the form of this. What would be the functional derivative? Let's say it should be Ck so power was 2/3, power was 5/3. So Ck 5/3 rho to the 5/3 minus 1 is 2/3. Okay, because there is no gradient, so ddx of f y prime, that term doesn't appear, but ddx of so f of y is this one. Do you remember I already told you how to get the functional derivative? What happened? Looking blank. Functional derivative, I had shown you the formula. So here functional derivative means I write this, your TTF rho is Ck rho to the power 5/3 dr. This was your Thomas Fermi kinetic energy function, isn't it? So if I take the derivative, so it should be f of f with respect to y minus ddx of f with respect to y prime. Y prime is not there in this. I will give you one which you have to do where y prime appears. But in Thomas Fermi theory, y prime is not there. So you can see this is Ck. With respect to rho, this is your 5/3 rho to the power 2/3. That's it. Perfect. Then plus V electron nuclear R. This is your external potential, isn't it? Because you see integral V En rho R dr. If you take this product rho R, VNR is constant, del rho 1. So you get VNR, and this one would be rho R prime. Now I can put R, or R prime is better, R minus R prime dr prime. This is your other functional derivative, isn't it? Is that J part, that operator part, and then multiplied by rho integral. So as we got this one, I will get this one. Okay, and this is your mu. So here you can see this is a deterministic equation for the density bypassing wave function. You know, first we defined the density in terms of wave function. But if we have to define density using wave function, obviously this whole business is not required. First I have to get the wave function and then I can do, then density is also not required. So I have to have There are several things coming into the picture. Density is good. We know why it should be used. We have to get the density from somewhere, but not from the wave function. So there must be some deterministic equation for the density, not by solving Schrodinger equation, get the wave function and then define and calculate density. No. Then obviously wave function is let's say 3n dimensional function. If I require something to explain using a 3n function, dimensional function, can I do the same job using a 3-dimensional function, density? That requires a proof. That I will tell you today. Okay. So these are various questions they were posed at that time. Okay. So now you can see this Thomas Fermi equation is the first what we call single density equation. So this is your single density equation, and here also this is orbital free picture. We are not bringing any orbital. So this is a single density orbital free equation, deterministic equation for the density. Okay. So in principle, if I solve this equation, I will get the density. Okay. After I get the density, I put it here, I get the energy also. Okay. In principle, all properties are density functionals. That we will see. So if I know the density, I know the functional form, I put it there, I calculate, I will get the corresponding property. Okay. But this Thomas Fermi theory, as I told you, it doesn't have exchange, everything is not homogeneous. You know the electron density in an atom near the nucleus, density varies very rapidly. Away from the nucleus it is almost constant, asymptotic. So if you take homogeneous electron gas, that means wherever you take the electron density is homogeneous, obviously that is a gross approximation. So you will not get, first of all, the atomic shell structures, etc. You will not get pre-Dell oscillations. All those important properties which you are supposed to get will be missing in Thomas Fermi theory. Okay. In fact, you can see in case of molecules, Thomas Fermi theory cannot predict binding. So there is no binding within Thomas Fermi theory for explaining the chemical bonds. So these are various shortcomings of Thomas Fermi theory, but people have started in along that line. So what was shown, say, in important cases, exchange. So this was also here within Thomas Fermi framework, like in case of Hartree theory, Fock could identify the drawback and put the exchange. Here Dirac did that. So Dirac exchange is a density functional, again you see, because it is within Thomas Fermi spirit. So here he had shown E exchange rho is minus Cx rho to the power 4/3 dr, and Cx is Dirac constant 3/4 pi 3 pi square to the power 1/3. This is a Dirac constant, and there is a minus sign. You remember the original exchange was also minus with a minus sign. Okay. So then you have inhomogeneity correction. This was given by so this is also called Weizsäcker correction. Have you ever heard of this name, Weizsäcker? No. So this is Weizsäcker correction is 1/8 grad rho dot grad rho by rho dr. So here you can see it is not only dependent on density but also the gradients. That means now you are putting that, no, everywhere it is not same. There is a gradient. But now you can see you have both the terms in the functional derivative. So this is your, say, you have to differentiate this with y prime. So if you do it y prime, it should be 1 by rho. This is grad rho mod square, let's say. That means 2 times grad rho. But if you, and then another term would be, the first term would be minus 1 by rho square, grad rho dot grad rho. Do you understand? And this one would be what? Minus cx 4/3 rho to the power 1/3. And if you put these also along with Thomas Fermi kinetic energy and other terms as I described, you get what is called Thomas Fermi Dirac-Weizsäcker model, TFDW model. So Thomas Fermi Dirac-Weizsäcker gives much improved picture. You get bonding, you have the oscillations, so many different things you will get. Okay. But these are the things which came long ago. They are called precursors of modern DFT. Excuse me. So they are precursors of modern DFT. Now we will enter into the density functional theory as we know. So density functional theory, as I told you, they are based on 2 theorems, analytically proven theorems that we will see. They are called Weinberg-Kohn theorems. So first we will see theorem 1. What is theorem 1? The non-degenerate ground state, write down, the non-degenerate ground state of any n particle system moving under the mutual Coulomb repulsion and a static external potential. Static external potential, let's say, arising out of a set of nuclei. Okay, that means this is your electronuclear attraction in case of electrons. Is completely characterized by the single particle density. Okay. By the single particle density. That means single particle density can give you, it was proven for non-degenerate, but later on Levy has extended it to degenerate cases also. Now what is the meaning of this? It is totally characterized, means we know everything about the ground state. What is the meaning of this? So firstly, what you can see in quantum mechanics, logically, we know everything if we know the wave function. Okay. In principle, if we know the Hamiltonian, we know the wave function. Whether technically we can solve it or not, we will be able to solve it or not is a different issue. But in principle, we can solve it. And if I get the wave function, I know all properties. How Hamiltonian is characterized, I told you already. N and VR, these two are sufficient to totally give you Hamiltonian. And if you get the Hamiltonian, that will give you psi, and that can give you all properties. Okay. And N, if you know the density from the normalization, we already know that N is already known. I won't have to do anything. If I know the density, I know the number of particles. So only thing what is problematic is the external potential. Because all others are dependent on only density. So if I know density, I know everything else. But external potential, that V external part, that is not known from the density. So what is the direct problem? I will tell you direct problem versus the inverse problem. What is the direct problem? Suppose I have a quantum mechanical problem, n particle problem. That means I know also the external potential under which it is, say, moving. That means I know the Hamiltonian, that means I know the wave function and all properties. If I know the wave function, I know the density also. Isn't it? I don't bother about this correlation, because if I know density, I can immediately, through a simple quadrature, numerical quadrature, I get the number of electrons. My question is with the external potential. So if I see that V of R gives me rho of R via Schrodinger equation, isn't it? Because if I know V of R and N, let's say, I get Hamiltonian, psi, and then rho of R. My question is, suppose I don't know V of R, can rho of R give me back the external potential? So the actual problem now boils down to this: whether density contains all information or not, whether density can give you the external potential, maybe within some additive constant. That constant you can always adjust, subtract from all, say, energy values, but nothing else, nothing more than that. So the inverse map is your DFT. Getting external potential from the density. And there comes your Hohenberg-Kohn theorems. So theorem 1 tells you that yes, density can give you external potential. Okay. What is theorem 2? So E rho assumes its minimum value for the true density. That means now we can have a variational principle that if you calculate the energy as a functional, that means the first theorem tells you all properties are density functionals now, because if density can give you the wave function, it can give you all properties, and I can in principle write everything in terms of density. So all properties are density functional. So energy is a density functional. So if I have some trial density, I know the formula, I put it there. The way we did the typical variational calculation in the wave function based picture. And then if I can minimize this, the minimum energy, the corresponding density would be my result for the true density. That means I have solved the problem and got the density. And because all properties are density functionals, I got all properties. Okay. So, second theorem tells you the variational approach, that the true density minimizes your energy functional. Okay. That means if you have some approximate density, you get the energy that would be always upper bound to the density coming from the energy coming from the true density. Is it clear? So, these are the two important theorems, Hohenberg-Kohn theorems. So, I will talk about the proof of the Hohenberg-Kohn theorem. So, first one is this theorem 1. Theorem 1 this is called reductio ad absurdum proof. Actually, this is a standard way of proving something, that you start from some assumption and then you do step by step logical analysis and you land up into a contradiction. That means you go to some absurd result. Then you tell that my original assumption was wrong. So, this is what we call reductio ad absurdum proof. So, Hohenberg and Kohn had taken that particular route. So, the first thing is we have to get the density will uniquely determine, maybe within some additive constant, the external potential. So, they assumed that let us say there are two external potentials and V prime R, and both of them will give you same density. That means density is connected to two different external potentials. Okay. That means density cannot uniquely determine your external potential. Perfect. So, that means this corresponds to, let us say, H, this corresponds to psi, and this corresponds to H prime, this corresponds to psi prime. And the corresponding energy, let us say ground state energy, I will call E0, and here I will call this as the E0 prime. Is that clear? Okay. This one is fine. Now, they had taken the help of standard variational principle. What is standard variational principle? Suppose I focus my attention to the V problem. Okay. V problem means what? My E0 is psi H psi. Of course, my E0 prime is psi prime H prime psi prime. Okay. But you see, both of them are connected to the same density. Although the wave functions are different, Hamiltonians different, external potential different, energy different, but they correspond to same density. Okay. Now first we focus our attention to this. And let's say we consider psi prime as a trial function for my psi problem. Okay, that means this E0 would be less than psi prime H psi prime, isn't it? Because from variational principle, if you have any other function, that will give you energy above E0. And similarly, of course, for E0 prime would be less than psi H prime psi, isn't it? Do you follow? This is just simple variational principle, nothing else. But this one I can write, this is equal to psi prime H prime psi plus psi prime H minus H prime psi prime. Okay. If you add these two integrals, you will get this. But what is this? This is your E0 prime plus, can you tell what is this one? You see, in H and H prime, only term which is different is the V containing term. Other terms are same, kinetic energy is same, electron repulsion is same. Okay, that means this one is integral your Vr minus V prime r rho r dr. Okay, let's say this is my condition 1. Do you follow? If I expand H, what I get? I will get the kinetic energy functional. I may write it in terms of one particle density matrix. Then I have electron repulsion and this external potential containing term. In other case also, the other two terms are same, only the external potential is different, so that term is different. So I will get this. Okay. Now you start from this one. You start from this one and do the same thing. Can you tell what is the result? That means you start from E0 prime, this problem. So here what you have to do, you take psi prime. Here we had taken psi prime as my trial function. Here I will take, where is the other one? Here I will take psi as my trial function. Then do what you get. Exactly do the same thing. Do it. Do all of you follow what is to be done? So first what we did, we started with E0 prime, E0 less than E0 prime, say E0 less than this quantity because it's a trial function, and then land up into this result. You start from the other component and take the other one as the trial function and do it. Tell me what is the result. In that case, what you have? You have H here, and here you have H prime minus H. Okay. So what do you get? So that one would be your okay. Not getting? You are not getting this? Got it? Okay. Just we have changed the variables, exact and the trial function. Are you getting, all of you? Okay. Not getting. Not getting. Got it? So if I add now 1 and 2, what do I get? Isn't it? This will get cancelled. So you are getting E0 plus E0 prime is less than E0 prime plus E0, a contradiction. That means our original assumption was wrong. That means one density cannot give two different external potentials. It can give one unique external potential. And that means one unique Hamiltonian, unique wave function, all properties are unique. That means all properties are unique density functionals. So that is the first theorem is proven. Okay. That's the first theorem. Second one now. So E V rho is what? T rho actually I am not writing electronuclear again. This is my external potential. Okay. Plus J rho. But at this stage, I will tell you that my VEE rho minus J rho is, I will modify this later. That's whatever I know about electron repulsion, whatever I can calculate using classical mechanics. So this is my classical electrostatic expression for the repulsion between one electron and a smeared out charge distribution, this J rho. But actually they are all interacting in a very complicated fashion. You have to take care of antisymmetry principle, etc., etc. So whatever is ignorance, I prefer to call it like this, is dumped into something which I don't know. That is, whatever I don't know is dumped into one place. This one I call exchange correlation energy. Okay. We will make further changes to the definition of exchange correlation energy as we go along. So till now, this is my definition of exchange correlation energy. So here I have to put or this is written V rho plus Here you can see this is T rho plus J rho plus Ex0. These three I am writing it as Hohenberg-Kohn universal functional. Remember, this is, you will hear again and again, Hohenberg-Kohn universal functional means, universal means this is only system dependent. It varies from one system to the other. These terms are same, whatever system you have. That's why this is called universal functional. This functional is same for any system you can think about. Okay, only difference is in the external potential containing term. And then I can get my del EV rho, del rho is del, so this one is what? We know this is your VR plus del F HK rho, del rho, and now I have learned how to calculate these functional derivatives. And this is your mu, isn't it? This is again, you can see the deterministic equation in DFT for density, bypassing wave function. So I know the exact form of this functional derivative. Okay. Where I take some form of exchange correlation function, this functional. Okay. Now suppose this energy, if I calculate for the ground state, I will call this as E0, and then I have some trial density, because I don't know this. I have to know this. So this trial density, I can put it over here. Wherever rho is appearing in this expression, I will put the rho tilde. Then I can solve this equation. And the corresponding energy what I get, I will call this, let's say this one, if I call EV rho, that's my ground state, exact ground state one. This one I will call EV rho tilde. You see the V is, which gives me the Hamiltonian, and this rho and rho tilde all integrates to n. So that means n part is same. So here what you can see, that V is same, that means this EV rho, if I call, that is for the exact density I am getting. So this one would be always lower in energy than if I calculate with any trial function. That means in all case, because this V is not connected to that rho prime, but this V is connected to that rho. Just now we have seen that that is the standard variational principle. So my EV rho should be less than equal to EV rho tilde. Equal to sign only when rho equal to rho tilde. That means what? Now I have a standard variational principle in terms of density. It's not that I have to go back, fall back upon wave function and see the wave function based variational principle. Hello? আমাকে জাস্ট 15 মিনিট পরে ফোন করবে? হ্যাঁ হ্যাঁ হ্যাঁ। So what do you get? You get a variational recipe now. So this is your second theorem. Not only we are entitled, but now second theorem gives me a recipe for the calculation of the density. That's the variational recipe. Okay. So this is something. Now what we can do, we can solve this equation that will tell that energy will be minimized along with this Lagrange multiplier, so the normalization also would be preserved. For at all stage, whatever may be my trial density, normalization is preserved, and I will get a solution where the energy is minimum. So that is the standard way of doing it. Now so far I have considered everything in terms of density. You see, this is my say DFT machinery, which gives me this equation which we can solve to get the density, and in principle I can write all properties as density functionals. Once I get the density, I will put it in that functional form, I will get a number. Okay, that is the value of that particular property. So this is in a nutshell your density functional theory. But how we do it? Like in Hartree-Fock theory, we went to, or Hartree theory, we went to the orbital picture. Can you develop some orbital picture? If you don't develop, then also the DFT is as such. So whether you go to Hartree-Fock theory, Hartree theory, it doesn't matter. You can go for the solution of Schrodinger equation per se. Here also this is the recipe what I told. So where you won't have to just bother about the orbitals. But suppose if you want to again develop, say further in terms of the orbitals, make a connection with day-to-day, say experience with the orbital based say mechanism, etc., or models, we want to go for this, and that is done through cone-sum method. So cone-sum scheme, I will tell you after the break. What is the time? So we will go for the cone-sum scheme after the break. Okay. So now perhaps you are getting a flavor of DFT, isn't it? So it is not just simply pushing buttons. It's a hardcore quantum mechanics, which you can understand now, but you can see that in principle you can talk about. By the way, one thing I forgot to tell you, that in Thomas Fermi theory, in addition, you have the electrostatic potential phi of r, which is say z by r minus integral rho r prime r minus r prime. So there is another, say del square phi is basically 4 pi rho r. This is what is called Poisson equation, and this one is called electrostatic potential. Okay. In case of molecules, you get MESP, molecular electrostatic potential, and that is one of the most crucial quantities in quantum biology, quantum biochemistry. Everything is explained in terms of the molecular electrostatic potential map. That you will see in some papers, molecular electrostatic potential maps. So this is within Thomas Fermi theory, you can just do it. In other places also you can do it. There is a del square phi as 4 pi rho. Okay, this is the solution of the Poisson equation. Okay, next person. For calculation, DFT calculations, what is being done? Actually, there this is called cone-sum scheme, or it is also called Weinberg cone-sum scheme. Okay, and this is basically your treatment within orbital picture. Now what Kohn and Sum did, see, if you have interacting electrons, obviously you will not get the orbital picture. So your interacting n electron system is mapped into a system of non-interacting electrons. Okay, so it is mapped, actual interacting n electron system is mapped into some system of non-interacting electrons. So here how it is mapped. Say H quantum let me write it like this: T or small t rho plus V quantum, where this one is some one body non-interacting potential. As they are not interacting, so it would be a one body only, and you define this way, and then you say that I can get kind of HI, KS, R, psi I R, EI, psi I R. These you can construct something like quantum equation, and these we will call quantum orbitals, and these are quantum orbital energies. Now how to construct this one, okay, and what would be the actual form, that we will see. So as you are talking about non-interacting electrons, we talk about S rho. This S means we are talking about all single particle case, okay. This one I will write it as sum over I psi I minus half del I square psi I equal to 1 to n. So individual kinetic energy for individual electrons. Okay. And in V case, I will put VR plus J operator. I am writing it like this: rho R prime, R minus R prime, dr prime, plus Vxc R, where Vxc is the exchange correlation potential. That means Vxc R is nothing but your del Exc rho del rho. where this is your exchange correlation energy functional and this is your exchange correlation potential. Okay. And this Vxc, we will define this Vxc in a moment. So first of all, this Ts is actually less than this, which we will call T correlation. So this is the correlation part coming out of kinetic energy. And you remember, I already told you that your VEE minus J rho, originally I considered this to be exchange correlation. But now what I will tell, in this exchange correlation, I will write EXC, what was there before, plus, so within quantum picture now, I have modified my exchange correlation. As I told you, whatever ignorance is dumped there. So this means it is J VEE minus J plus T minus Ts. This is your exchange correlation. One part is coming from potential energy, one part is coming from kinetic energy. Do you understand? So when we talk about exchange correlation energy, there are two components. One, because we considered, let's say, Coulomb repulsion as a repulsion with some smeared out charge distribution, but actually we have to take particle by particle and also the Pauli's antisymmetry principle. So whatever is not known, that difference with exact electron-electron repulsion and this Hartree potential is my exchange correlation, I told you before. But now I can see that if you go to the orbital picture, you have to add something else also for redefining. So when you do the actual DFT calculation, basically I am taking EXC where there are two components. One is from the potential energy, another is from the kinetic energy. Do you understand? So here these psi i's are quantum orbitals. But in actual case, what it should be? It should be psi x1, x2 up to xn, then psi star x1 prime, x2 up to xn. It should be a density matrix. But in quantum picture, we just get away with that complicated description. We are having simple orbital based picture, and whatever is missing, I dump it in the exchange correlation energy. Okay. So if you take the functional derivative of this, what you get? How do you take the functional derivative of this? You have to take the derivative, let's say, with respect to density. If you take, so you take the derivative with respect to psi I, and then take the derivative of psi I with respect to rho. So chain rule, and with respect to psi I, if you do and you take this one, ultimately only minus half del I square will be remaining in the equation. Then with this equation, which we will call quantum equation, plus V effective R psi I R as EI psi I R. So these psi I R's, these are your quantum orbitals. So and you have one let's say one body effective potential in which all electrons are moving and the electrons are not interacting with each other. What are the components of your V effective? You have external potential, you have Hartree potential, and you have exchange correlation potential. That's it. Okay. So this you have to solve iteratively. If you solve them iteratively, how do you solve them iteratively? If it is a case of molecules, you have to start, are you telling something? You have to start from Born-Oppenheimer approximation. That will fix my external potential. Born-Oppenheimer approximation, nuclear frozen, that will fix my small Vr. Then I start from a set of trial functions, and rho of r is simply sum over I psi I r mod square, I equal to 1 to n. Okay. So if I get this, what is my V effective? You remember, V effective is V of r plus r prime, r minus r prime, dr prime plus V exchange correlation. Okay. So what are the steps I will be doing? Step number 1, start with some trial quantum orbitals. Okay, any function, like, or I can expand any orbital as a linear combination of several basis functions. Okay. And some accurate but approximate so you can see these are the two cornerstones of any calculation, even wave function based calculation also. You have a basis set, you have energy functional now in this case. It must be accurate but approximate. Why accurate? That I must have this analytical form derived from some theory. Okay, I may take B3 leap, I may take PW or PB, whatever I take, that must be derived from some, but that is approximate, we know, because the nature of this is approximation. And some basis set to start with. We will talk about basis sets and functionals in one of the, I will get only 2 more classes. So I will tell you, okay. Then second stage, construct V effective. If you get, no, your third stage is get rho of r. If I know this psi I know the density. Then third stage, construct V effective r. These are your quantum equations. So for all I, these are your Ks equations. Perfect. So you can see now what I have done. I have started with some guess basis functions or corresponding orbitals, constructed quantum orbitals, and some approximate but accurate exchange correlation potential or energy, get the density out of my trial function, and then construct V effective there. Okay. This Vxc will also depend on density. because your E x0 is a density functional. So if you take the functional derivative, it also will, but if you know the density, you know, you can calculate this, you can calculate this, and you know the potential, external potential. Okay, so the effective potential is known to you. Then fourth, solve Kohn-Sham equation 1. If I solve this for individual electrons, what I get? I get psi i's and E i's. Okay. This iterative technique we have learned enough. Okay. So I will go to the next stage of iteration. I will get another set of psi I and Ei. I do the same operation again. After solving this, I go back to this. Rather, I go back to this. Okay. With the new set of psi i's, now I again construct the corresponding density, then effective potential, again put it back. I will get another stage of iteration, I get another set. I keep on doing it until the energy values for all orbitals in two successive iterations are within certain prescribed limit. Perfect. So we will say the Kohn-Sham equations, they have now converged. So we get converged Kohn-Sham SCF orbitals. Now it is SCF procedure. Kohn-Sham SCF orbitals and the corresponding orbital energies, depending on whether it is atom or molecule, and that your this VR will determine whether it is atom or molecule, and then we will tell them the molecular orbital energy or atomic orbital energy. Perfect. So that is the way we solve. If you want to get the corresponding wave function, this is called Kohn-Sham determinant. So psi d 1 to up to n would be 1 by root n factorial, and then you have psi 1 1, psi 2 2 up to psi n n. This is your case determinant. But these are your SCF Kohn-Sham orbitals. So that is your Kohn-Sham wave function. With Kohn-Sham wave functions, now you can calculate whatever property you want. Actually, what will happen? With this, you get the density. Sometimes we need wave functions. Where will we need? If you know the density. When we require, suppose we are talking about spectroscopy. I have to have a transition from one state to the other. Then I have to have some kind of state. That means this type of functions are required. There we make use of this. Okay. Or suppose you talk about TDDFT for getting excitations, etc. So there the density is not exactly the right quantity. So you go from one state to the other. There you require this. Okay, but that is also pretty simple. You are not doing any extra computation. So these are the Kohn-Sham equations. In actual DFT calculation, you solve these equations self-consistently and iteratively. The first thing what you can see, that even for a many electron system, we are within a single electron framework. That means the computational labor wise, there is a drastic reduction. And otherwise, if you see that if I write my this H effective, if I call H effective I, this is like your H naught in Hartree theory. In H effective there are three terms. One is minus half del square, and then this one, this one, this one. So you can see that the first three terms of H effective in Korn sum, they are same as in the first three terms in Hartree-Fock theory, isn't it? So if you have understood Hartree-Fock theory, the first three terms are same. In case of Hartree-Fock theory, there was one, say, integral operator, exchange operator. Instead, you have a density functional sort of stuff, exchange correlation potential. So there you have to have coupled equations. Why? Because your exchange operator needs the information of all the orbitals. Okay, you cannot do it with the density. But here you can see, because I am writing exchange correlation potential as the functional derivative of exchange correlation energy, the computational labor is of the order of that in Hartree theory, not even in Hartree-Fock theory, Hartree theory, isn't it? Because there you have to do so many coupled equations you have to solve. Here you can do it one by one, slice by slice. Okay. But it contains correlation, which was not there in Hartree-Fock theory. So although we are doing it, the computational labor is at the level of Hartree theory, we are getting our results better than Hartree-Fock theory. That is the beauty of density functional theory. We are getting correlation also, isn't it? And we solve these equations, which is allowing us to get the solutions for very, very large systems, which is not possible in any other. Even in certain cases, Hartree-Fock theory is also very much computer savvy. So you have to have very computer demanding sort of stuff. The computational economy is much more over here, and accuracy in most cases it would be better. So if you can have a proper exchange correlation functional, you can get much better accuracy than in Hartree-Fock theory. But the exchange approximation is such, sometimes you will see that the energy values are not coming, where exchange, particularly for the systems where they are very, very important. In that case, what we do, in addition to this, we also put a part of Hartree-Fock exchange, and we define what are called hybrid DFT, where partly Hartree-Fock, partly DFT we are doing. You are doing calculation, you must have heard hybrid DFT, isn't it? So there a part of Hartree-Fock exchange is also included. Say if you have like B-leap, that is simple exchange and correlation, but if you go to B3 leap, there you have part of Hartree-Fock exchange is also there. This is a hybrid DFT. Okay. I will talk about GGA, meta GGA, all sorts of stuff. But in principle, what we are doing, those are the steps which we are following. So when you give the computer or your software the commands, it is following exactly those steps and giving you the result. And after getting the density and energy eigenvalues, we will talk about these energy eigenvalues later. How much is the time? Maybe I can tell you a little bit now itself.
11:47.
Okay, so I have time. So here what is happening, that in case of Hartree-Fock theory, there is, I will tell you, now Hartree-Fock theory, you get something called Koopman's theorem or Koopman's So in Koopman's approximation, what happens? Say you have the Hartree-Fock energy levels, let's say E0, E1, E2, etc. And up to this, let's say they are occupied if this is a restricted Hartree-Fock. This one we'll call HOMO, highest occupied molecular orbital. And this one we call LUMO, lowest unoccupied molecular orbital. The Koopman's theorem tells that if you want to, so these orbital energies are same as the energies required to knock out the electrons. That means the corresponding ionization energies. And if you want to put an electron over here, that would be the corresponding electron affinity. Okay. That means this, in standard neutral, let's say, system, your negative of HOMO energy will give you the ionization potential, and similarly negative of electron affinity will give you the LUMO energy. That means if you have solved the Hartree-Fock equations, you can get already the electron affinity and ionization potential. Is there any similar theorem? So you get something called a Janak's theorem. In case of cone sum orbitals. Unfortunately, for cone sum orbitals, only the HOMO energy is equal to the ionization potential. Rest of the orbital energies cannot give you the corresponding ionization energies. So here, like if it is Hartree-Fock theory, if you want to take out an electron from this level, the corresponding energy required would be just negative of this much. That is ensured by Koopman's approximation. Of course, this is approximation, but in most cases it gives a reasonably good result. But in case of cone sum orbitals, unfortunately, you get only but the HOMO energy and the corresponding ionization energy that matches very well, but the other, there is no correspondence. Okay. So I think I stop today at this point. In the next class, if time permits, I will tell you about the basis sets and functionals, various types of functionals and so on. Okay. Yes.